Welcome.
Oh, you want this?
It's fine.
Yeah.
Hello. Wow. Yeah, this will work. Welcome to theory seminar. We are from Georgia Tech talking about robustly learning affine transformations. She will be visiting us for the next sem, so be on the lookout for her. And
Yeah, if you find this talk interesting.
yeah.
Thank you. Thank you for the introduction. Yeah, so I'll talk about robust way learning of affine transformations. So this is just a second by this year Fox. And this is joint work with Pravesh Kodara. He's a assistant advisor at CMU, and he's moving to Princeton next year. And my advisor, Santosh Kampala at Georgia Tech. So if I have any question, please interrupt me and ask. Okay, let's first see what is affine transformation. So for our goal, we are trying to learn the specific case that's affine transformations of hypercubes. And general definition of affine transformation is just like a transformation function. So we have points x, and so for point s, so we assume s is taken from the standard hypercube. So on each coordinate, it is uniform from interval -1 to 1, and it's a product distribution of all coordinates, all d coordinates. So d is the dimension here, and we transform it. So first transform it by a full rank matrix A, capital A, and then we translate it by a vector small b. So our goal is to try to recover these two vector small b and the matrix A. So these are these things we don't know. The only thing we know is we have those samples after transformation. So those samples, those x.
You know the S.
No, you can say we know the distribution of x. We know x are from the standard hypercube, but we don't know what they are. So what exactly are those points? We just know they are from uniformly from the hypercube. And there are three types of affine transformations.
In the sense that it could be some affine beta in which also.
No, it's yeah, that's the point. They are not unique. So I didn't mention what's the exact our goal, but our goal is not to recover the exact all the exact same of B and A. That's the some in the total variation distance close to the small x, the distribution.
And yes, just pedantic question. If I knew S, then this would be an easy problem. It's just inverting.
If you know what?
If I knew S, if I had like linearly independent collection of S's, then this should be a
so if you know small s and x.
yes. Many such S, like different samples.
Yeah, that's also I think that's the different question, but that's also interesting. We can match them. Yeah. But here we only know x. We can only see the x. Those are our samples. So three types are the translation. So we just translate in some direction. The diagonal scaling, all scaling, but the figure here is just a diagonal scaling. So we only do scaling in the coordinate directions. And the rotation. So we rotate it some. Yes.
We know that S comes from this hypercube, but we also know the distribution.
Yes, it is the uniform distribution over this hypercube. So it is a known distribution. We just the unknown thing is the transformation or the transformed distribution. So after, and if you think that this after transformation as a polynomial cube, then it is a parallelograms in 2D and is a parallel path in high dimensions. So it's a polynomial. And here's our problem. The samples are just ID points from the affine transformations of the standard hypercube. So all you can say is the parallel paths after transformation in high dimension. And our outputs will be the estimated A and estimated B. And our goal is to get the transform cube should close to the unknown cube in total variation distance. So total variation distance, because we are in a special case that the distribution is uniform, then it just equals to the maximum of these two cases. Either it is, so suppose H is the true cube and H hat is the cube output, then the total variation distance should be the maximum of these two, whether it is the distance of the blue cube over the volume of the blue cube, or is the orange, the volume of these orange parts over the volume of the orange cube.
Is there a, should there is bit, why is this the metric of choice? I could have, for example, looked at Frobenius distance between A and B naught or some. Or
Yeah, that's good point. We can look at it, but it turns out that's something easier to do. It doesn't give us. Suppose we have a good estimation of A that is close in Frobenius norm with the, but it doesn't give us the total variation error guarantee.
Okay.
It's actually much worse than this total variation error guarantee. I'll talk about that later.
So this implies progress. So
Yeah, in this, it implies that the very good Frobenius norm guarantee, and also for capital A and small b, both of them, the parameter recovery. I mean, not exact because you just mentioned those are not unique, but with some proper computation.
but I'm just trying to appreciate like the significance of this metric, and probably the point is that if you want to sample from H, this H hat is a good. And so is that the reason for looking at this particular metric? Right. So ideally, you would want to sample from this unknown.
Yes.
Yeah, translate.
So one thing is TV distance is always the natural thing to do, and the other thing is this is the optimal measure we can get.
Yeah. So the only sort of reason I'm harping on this point is TV distance is typically for probability measures. It's a distance metric. But now you're looking at it as a volume, but that's okay. So you're just saying if you were to uniformly sample from H versus uniformly sample from H hat, what would how different would those distributions? Is that the?
I mean, it's the same thing.
Okay.
We get this volume thing using the definition of the probability density. So it's equivalent.
Sure.
Yes. So we want to learn the Affine transformations because first, this is an important setting for independent component analysis or ICA. So we are trying to find all the independence, or we can say in this case is the coordinates of cubes. And this is also a special case of learning intersections of half spaces or polytopes. So both of those problems are hard, especially learning polytopes. But hypercube is an easy case for this. And this is the previous results of previous algorithm, how we can learn fine translations. So the most easiest thing we can think of is just use the method of moments, because the first 4 moments is proof that can uniquely determine a hypercube. So the first moment or the mean will correspond to the translation of the small vector b. So if we can suppose this blue cube is the standard hypercube, and its orange cube, if we estimate, compute the empirical mean of this cube, then we just get what's the translation vector. And similar for the scaling case, if we compute the second moment or the covariance of this distribution of those samples, then we'll get what's the scaling factors in each directions. And the fourth moment or the rotation is a little bit harder, and it's shown in the work I'll just mention. So it proves that if we get the fourth moments, then we can learn the rotation matrix of the fine transformation. So Freeze, Garam, and Cannon, they gave the results. The local maximum of the fourth moments are exact directions of normals of facets. So if we first make the cube isotropic means it's already in a good position. The mean is 0, and the covariance is identical.
For the hypercube, this is already true.
For hypercube, yes, it is true, but here we are learning after the transformed cube is not always true. So it means that
You say the cube is isotropic, the translated.
Oh yeah, the translate the
H.
transformed cube, yes. All it means we make it no shift or scaling, just rotation. So it says that we can learn rotation by finding the local maximum of both moments.
What is the local maximum?
So both moment is a tensor, and if you can think it as a function that's on the directions, and on each direction gets a number of the both moments in that direction.
Like the generalization of a bilinear form.
Yes.
Both moment is a tensor, but it's a fixed number. It's just a.
In different directions, yeah, it's a fixed number in fixed direction. So we just want to find direction that it is maximum.
Oh, okay. So you look at the tensor, look at directions where it's locally optimal, and those directions are the constant.
Yeah, you can think. So for example, the cubes, there are 2 special kinds of directions. One is the facet normals, and you can think, oh, those are where the fourth moments is maximum. And maybe also the orthogonal, the diagonal directions that points for some vertices. That's somewhere it will be minimal.
Yeah, at least in this thing, I think if you look at the form, it looks like VI or VI or VI as a basis. So when you try to maximize any direction, you right, it will pull out one by one of the bases.
So say that again. It's VI
VI output and VI output, VI output. Some of this, that portion tensor looks like in this condition under these assumptions. So when you try to maximize it, you have to pick X to get right. That will be a local maximum. One by one, you get full of this.
Yeah, so this term gives us a non-robust algorithm. So we first make the distribution of the sample isotropic, and by this step we can learn the mean and covariance. So we can learn the translation vector and also the scaling factors. And second step, we just find directions that maximize both moments to get all facet normals.
Isotropic just means that it's not general position. There's enough volume in every dimension.
Isotropic means that you have zero mean and identity covariance. That's the definition. Just because this. So it has same mean and same covariance as the standard hypercube.
But when you say the cube has this, it means the uniform distribution on the cube.
Yeah, I use those words that. But what if in our samples there are noise outliers? So we introduce the robust setting. And we are trying to learn with in our sample, there is a constant fraction, and we call it epsilon. So epsilon fraction of data is arbitrarily corrupted by the adversary. So it is arbitrarily corrupted means that the adversary can do anything to our sample, but within the epsilon fraction. So they can add outliers, remove good points, and they can first look at all our samples and decide to do what to either do these two kinds of things. And our problem for this talk is to estimate the affine translation so that our resulting distribution is within PV distance all of epsilon of the annual transformation. So these
Absolutely optimal we can expect.
Yes, I'll explain this. I say that this all of epsilon or linear epsilon is the optimal error because you can imagine that the adversary can modify epsilon fraction points. So what they can do is just replace our cube with the PV distance epsilon, another cube with a PV distance epsilon. And the sample will look like exactly from that cube, but within actually it creates the epsilon PV distance error.
And my question was like, what is the optimal we can expect? Like, is there a
So it can't do better because of the.
What is the in the non-adversarial case? What is the optimal guarantee?
Oh, in non-adversarial case, the non-robust case, we can do as good as you want, just with more samples, more running time.
Okay, so there's no.
What he's saying is you cannot do better than epsilon. They are getting order epsilon. That's what she means by stuff.
Okay. So it's not like a sample complexity boundary. So it's not like if the number of samples is as.
Oh, even if we add more samples, we can't do better than this.
Okay, sure. I was asking the quantitative relation between sample complex, the number of samples and the TD distance.
Oh, I understand.
Non-adversarial.
Yeah. Here we didn't use that because this is the upper bound of the error. It's bounded by the fraction of corruption. Even if we use more sample, we can do better. So that's why it's just epsilon. There's no sample size or running time. And let's see some previous results, what we can learn robustly and efficiently. So first thing, even learn a single Gaussian in high dimension is non-trivial. You can't just use the empirical mean as we usually do. A single outlier can corrupt every moment. And also the high dimension mean estimation needs some novel methods. And here are two results at the same time. So one by Nicholas command Kane, Lee, Martin Stewart, and the other one by group Lai, Roy, and Van Pala. So they both prove that the means, and if we think covariance is at mean, then we can learn those parameters robustly within the error. All of epsilon times square root log 1 over epsilon. So it's almost epsilon. So it's poly epsilon and in polynomial time. So here we need distribution to be nice. This means it has bounded higher moments, so bounded covariance and bulk moments. And we'll also use the results to first get some estimated mean and covariance of our distribution. And let's see the first attempt. What if we just replace we have a good non-robust algorithm. Now we can just replace those empirical moments by our robust moments. We just see there is a good robust moments estimation algorithm, and we replace those empirical moments by robust moments. Can we get a good enough algorithm? Unfortunately, it doesn't work. Because as I just mentioned, the robust estimators can only give us poly-epsilon accuracy, and this we can't improve because the adversary can always multiply epsilon fraction points. But this poly-epsilon accuracy is not enough in application. They need something 1 over the accuracy of those moments to get the PV distance bounds. So our second attempt, we can use the very popular used robust method of moments, or the sum of squared methods. There is a result by Kodar and Spira. They gave a robust algorithm to recover the linear transformations it has. So they only focus on the linear transformation because they don't want to recover like using the total variation distance metric. So the robust moments estimation algorithm already gave them a very good estimation of translation. And they gave the error guarantee of this algorithm is each column of A height is close to the corresponding column of A up to the poly epsilon relative error into null. So it says that we can learn each column or each row of A that's within 2 null. It's not same as the forgiveness norm, it's even worse than that. But it's something that's good because it's independent with the dimension. So our goal is we don't dimension in our error guarantee. Dimension is too large. We can't afford that.
Like the fact that this is just a linear translation, like B is not an issue. Like
B is not.
It's just a mean. So
Yeah. I can do the robust mean estimation. That's good enough for them. They already get a good parameter distance.
So if you just wanted like some matrix instead of PV distance, some matrix closeness like AB close to A hat, this would suffice.
Yes. Yeah, this gave us a good parameter distance estimation. And they use the sum of squares method, and the algorithm is just use the robust estimators for moments, and based on the method of moments, they match those moments and also some other properties of the cube distribution.
That's the reason for sum of squares. Like they want both moment and
yes. So they use sum of squares in a way to how to choose those good points. So, and this is also a good start of our algorithm because they gave those, we know the rows of A, if we ignore the scaling parts, the rows of A are exact vertices, not vertices, the size and normals of the cube. So we can use those as the starting point or one start of our algorithm. I'll talk more about why the parameter distance doesn't imply the TV distance.
Yeah.
So
this parameter.
a parameter distance means just distance between A and small b. we call those parameters A and B, and distance, parameter distance, just distance between the true A and the estimated A, and also the estimated small b and true translation vector B. Yeah, so parameter distance, yeah, you can also use different metrics, L2 norm, valence norm, but it's just distance that's between parameters. So we prove this theorem that suppose H is the standard hypercube, and now A is a rotation matrix. We don't need it to be an exact rotation matrix. We just assume that is a matrix with unit rows. So each row is has a norm 1. Then we apply A on H, and the TV distance between AH and H will be tightly bounded by a constant times sum of two norm between AI minus EI. To recall that this is exactly the thing, the guarantee we can get from their algorithm. But there are guarantees we can bound this by poly epsilon. But we can see if we add them up, we have at most d dimensions. So if we add them up, we can get at most d times poly epsilon that is too large for TV distance. D can be very large, they are in high dimension. It is upper bounded and lower bounded by this. So this told us the TV distance, our guarantee requires a bound on the total sum of the L2 errors across all rows, not the sum of squares of L2 errors. So the sum of squares is just a Frobenius norm. But Frobenius norm is not enough. Even Frobenius norm can be small, but the sum of L2 norm sometimes can be large. And this is another 2 examples why the moments are not enough. So this one, we translate the cube by distance epsilon to the diagonal direction. So imagine we translated to a direction of vortex, some vortex. Now we can compute in each coordinate how much we translated. So because this is epsilon, and then we can compute in each coordinate, it's translated by epsilon over square root d. And now what's the TV distance between these blue and orange cubes? So the overlap will be 1 minus epsilon over square root d to the power of d. And the TV distance 1 minus overlap, it will be almost epsilon times square root d. So again, it has a dependence on dimension d. But note that the only moments that are different is the first moment, the mean is different by epsilon. We only do a translation of epsilon. And all the other higher moments are same. We don't change the shape, just translate it. So this example shows that even we can learn all moments of the cube perfectly, still we can avoid this dependence in total variance distance. And this second example shows that even if we assume that we know the mean, now we are not in this, we try to avoid this case, suppose we already have the mean, but still, if we do this rotation, we rotate it by an angle epsilon, then the TV distance again is something epsilon times d. And we prove that any moments of order t equals to small of log d over log d is not adequate to learn the rotation. So this is something, if we want to get the moments of this order, it already requires some exponential time to do this, because it's a log d, almost log d order. So we have to find some method that's beyond moments. There is a very simple but inefficient algorithm.
Good question. So far, what you have discussed actually has not used hypercubes very great extent, except maybe the last time. Like the Steuer and all, put Harry Steuer work actually is a general, two general distributions. But just,
No, they only, that was the moment works for hypercube.
oh, even
So the product distribution of them, not type, but has to be a product distribution of some bounded distribution.
and so in some sense, can we also infer the other direction? That is, if I were to give you a good EV distance estimate, that would imply good matrix. I mean, that would probably just follow from the theorem.
If you have a,
If you have an H hat which has low TB distance to H, then in some sense you have estimated the matrices rather well. The Frobenius norm has to be small, cannot be that.
if we have the,
If you have small, if you have an upper bound on TB distance, does that imply an
Yes.
upper bound on Frobenius norm?
yes. Yeah, but not the other way.
Generally gives you the other distributions as.
Yes, yeah. So it's yeah, if we have the TB distance, we can get the parameter distance, but if we only have the parameter distance, it doesn't give us the TB distance.
Which is the quantitative form? What is the quantitative version of that statement?
What's the,
Is like if TB distance is alpha, what can I say about, let's say, the L2? It's just the sum of L2 is L3. Is it most that
yeah, this is a highest bound, so that's what we can get. But you can see this is not any commonly used metric. They're not sum of L2 norm of each row. This is not Frobenius norm or any other.
yes, probably that's what I'm asking. Is there a way to connect it to those metrics?
This is the highest bound, so there's a best way to do it. And for the mean or for the small vector B, that is L1 norm. We that connects to the L1 norm, the TB distance. TB distance tightly bounded by the L1 norm of mean. So suppose we have those samples, and inefficient algorithm can be, we just find the smallest cube containing at least 1 minus the epsilon endpoints. We try to find the, we want to cover 1 minus the epsilon endpoints. That means the TB distance between the cube we find and the true cube is C epsilon. And also we found the volume of it because it's the smallest one. But however, this algorithm is it takes exponential time because we have to try out all sides of 1 minus the epsilon points and see it gave us the smallest volume.
Just like, that's probably naive like implementation. And this Is there no better or like can't you use it as some sort of a coverage problem or
So how do we find the, yeah, we use that idea, but I'm not sure if we can directly do this. And you have some efficient algorithm to directly find all this too.
let me ask like probably a digression, but if I look at it not as a sample set of points, but so it's a more of a decision with combinatorial optimization. But I give you some set of points in, and there are no sample nothing, and I ask you to see is it like possible to do like a hardness result, like NP hard or something.
I don't know. I think it's gonna be hard. We know nothing about those points.
Just asking like so this is a combinatorial kind of a problem. I give you, so forget the context that these points are coming from a distribution. Your input is just a set of points n. So you have a target volume, say gamma. Is there a cube of volume of gamma? That's like frequencies, like a coverage problem. Think of it as a set cover problem or like a max coverage problem. I give you these many hyperplanes. Instead of count, I'm giving you a volume. You now it's a max coverage problem in a volume sense. Those guys have a very good approach. If one might.
I think if you can solve this, then we can solve the quality of learning problem. And the quality of learning is actually very hard to do.
But there are again like the fact it's a hypercube and all that.
Okay, I see. So just find the hypercube.
Yeah. I'm not saying it's an easy problem.
Yeah. Yeah, so we'll use this idea from the inefficient algorithm. Now our goal is to make our cube have more points, while the volume, we try to keep the volume low, say low. And this is an idea that there's no moments, so we just update our current cube to add those high density parts and remove the low density parts. And this is our main theorem. So we show that suppose we give the samples, corrupted samples, have some corrupted samples from the unknown public pivot, and we give an efficient algorithm that outputs the estimated parallel types with our guarantee that PV distance is all of epsilon. And our algorithm has two parts. The first one, we deal with the shift and scaling case. And in this case, we assume there is no rotation to focus on the shift and scaling. And second one, we focus on rotation, assume that we already have the mean and covariance. And both of these two algorithms use the same idea. We update the current cube and to get more points in the cube. And there is one important thing or step in our algorithm is the filtering step. Because for both algorithms, we actually update the cubes in 1D. We do it in low dimension. But now there is a question that's because we update the 1D parameter separately. What if there is some there's some noise that's in the intersection of different coordinates, and it will have effect on all coordinates. So our filtering step will deal with this bad case. We'll check every intersection of two coordinates. If the points here is has high density, so higher, much higher than the correct density of a hypercube, then we'll remove all points here. We'll do this for both cases, for both shift and scaling and rotation case. And so after the filtering, we want one condition is that this intersection has a good density that is bounded by this, the thing here. So the density of the intersection is bounded by the density of 1D slab times the density of the other in the other direction density, and with some constant multiples. Suppose we have this, then this lemma says that we can bound the sum of all the arrows by the union of the arrow. We know that union of the arrows of outliers is epsilon. The others we can at most change epsilon fraction points. So this lemma is a reverse of the unit bounds. We can see in this conclusion, the left-hand side is the sum of something, sum of probabilities, and left-hand side is the probability of the union. Epsilon is the union of SI. So here I use the fraction of XI. It's a bit weird. You can think it as a probability. So the probability that we take a point from this set SI. Because we can make alpha epsilon a constant, for example, 1/2, then this right-hand side is just 2 epsilon. So we bound this the sum of fraction SI by 2 epsilon. Proof of this lemma is easy. We can use some IISc inequality to prove. I don't think I have time for this. Just skip this. But let's see why this lemma or observation is important. So we can think those SI to SD are outliers. So those are the bad points we don't want. And we are trying to use this lemma to bound the effect of outliers in total in each direction. So the left-hand side is in each direction. When we do the 1D updates, it gives us SI of fraction SI arrow. So the total arrow will be sum of these. We already seen the theorem that the TV distance is bounded by the sum of in each coordinate. So we just do is bounded by the sum of these, and the sum of outliers or arrow in each direction is bounded by the union of them, constant times the union of them. So that's enough for us. We already get a C epsilon bounds. If we have this important that we can do the 2D, we make sure each 2D intersection has a small number of points. That's enough. That's why we do the 2D filtering. So now our algorithm can be in a very low dimension. We only check our 1D steps to do the 1D updates, and we check the 2D intersection to make sure that number of points is small to make to have this condition satisfied. Now let's go into the two algorithms, how we can do the 1D updates. The first one, for the shift and scaling case, we'll learn the thresholds in 1D. The threshold means this. Suppose we project all points on this direction. Now it's just a 1D density function, and we want to get 2 points on this 1D line. So one is the upper bound of the points, and the other one is the lower bound. That gave us 2 facets of the cube. because we already know all the correct facets almost. The only thing we want is what's the threshold of those directions. So we project all points in this direction, and we check number of points in each 1D steps. So it looks like this. So this is a 2D figure, but you can imagine in high dimension it's a hyperplane thing. At the boundary, we take a very small distance and we count number of points here. So if the point here is at least half of the expected number of samples, then we'll keep this. So if it is not, so points here is too small, too few, then we'll move the boundary towards the center in the violating coordinate. So we'll, for example, if there's no point here, then we just move the boundary to the to here, to this next threshold. And of course, we continue to do the filtering thing whenever we move the boundary. So in this way, we'll update each threshold in each coordinate until we get correct cube. That give us, for every boundary, it has high enough density. And this is the shift and scaling algorithm. For the rotation algorithm, we also do the 1D updates in a different way. So now we have to learn the rotation or the rows of the rotation matrix in 1D. This is the, again, we'll do the filtering step, and after the filtering step, what we do is we collect the points. So orange is our current cube, is our estimated cube, and blue is the true transformed cube. So there will be some good points outside orange cube, but inside blue cube. So this is the part we focus. We'll compute the robust mean of these parts, call it Q times mu, and we'll update our height to the opposite direction of this mu theta, so to the minus mu theta direction. So we prove that if we continue doing this, we'll get the height A will be close to the true direction of the facets. We'll keep doing this until we find in this direction, we'll find a good row of height A, and we'll continue on this next direction, next facet. And we call it robust gradient descent. It's not exact gradient descent, but we update our rotation vector using the mean of the points outside. So the point here, again, is to try to include more points in the cube. And that's something we want to optimize it. And how to do with the general case of all the compositions of shift scaling and rotation. So first, we have the warm stars. We can get the estimators that's polyepsilon close to the ground truth by the algorithm that I just mentioned. And learn all the mu, the covariance, and A for each row of A. And now use the warm stars. We can start our updating algorithms. We alternate between the shift and scaling and the rotation algorithms. And the number of samples inside our cube is at least 1 minus C epsilon n. So this is the point we know that if the cube has this number of points, that means the TV distance between the true cube is at most 3 epsilon. So we want to make sure that we have enough samples in our cube. And if not, we can improve it by our 2 algorithms, shift and scaling and rotation. So the good thing is both of these 2 algorithms create some error. So it has some error guarantee. But so when we do shift and scaling, we know we have some error from the rotation because we don't have the exact all the facet normals. We can only use the estimated one from our rotation algorithm. But the good thing is by one round of shift and scaling and rotation, we can reduce this error with some constant factor. So suppose in one step we get delta error, then in the next iteration we'll reduce this delta to delta over 2. So at the end we'll go to the error of the constant epsilon. And in summary, I talked about the method of moments is inadequate for our problem, this robustly learning parallel path. Because there's first the theorem told us that the bounds, the TVD is bounded by the sum of L2 norm of rows and plus the L1 norm of the means. So we use the some techniques beyond moments. We use the filtering step and robust gradient descent. Combine this with the 1D check of the cubes to get a good estimation of cube. And it's actually a practical algorithm with fast runtime. I mean, the sample size is all of the square of V, and runtime is same, is linear in the sample size. So it's just almost D square time. It's faster than the SOS based algorithms. And there are some open problems or the future directions extension of this problem. The first one is the works I mentioned, those FJK and also Kodari work. They work for the product distributions with both moments are different from Gaussians. If the both moments is same as Gaussian, then we can't distinguish the coordinate directions. But if they're different, that means we can learn the product distribution. So can we do the same thing? Can we robustly learn such product distributions? And also, can we generalize to some polytopes with some restriction? Of course, we can't learn any arbitrary polytope, but maybe if we have some condition, so my guess is if we know the angle of facets, so angle of each pair of facets, we know if the facet normal, suppose those are AI AJ, then if we know each pair of them, AI inner product AJ is bounded. It's bounded, so it's almost orthogonal. So first condition, and we know that each boundary is large enough, so each facet has large enough value, then we can learn such polytope. And the other direction is that we call it statistical learning. So still it's robust learning, but it's a very different setting. In our setting, we assume the fraction of noise is really small. It's a small constant, usually less than 0.5. But now if we are told that the fraction is large, small and half the point are corrected a noise, then how can we do learning? Of course, we can't get a good estimation of point, but can we get a list of basis of size? So the list has a size of 1/1 minus epsilon. 1 minus epsilon is the fraction of foot points. We get a list of size 1 over the fraction of foot points. And the error guarantee should be at least one of the inside this list is a good estimation of the true distribution. So this is another also robust setting of those robust learning problems. And can we solve the problem in this setting? So that's the question. And that's all. Thank you. Any questions?
Last problem you mentioned, so does the Kotaris algorithm work in this setting? So the listing of the setting?
No, we need, I think we need very different algorithms in this setting. And the thing is, we don't even know if we have a bound on, equal theoretical bounds for these. Is this size enough to get a good results? That's the thing. I think we need something to have those. For example, for Gaussian, so here's the thing, because the adversary have more power to manipulate the samples, so they can add. Suppose the fraction of clean data is alpha, then they can have 1 minus alpha. If alpha is 0.1, then they can add 9 of different cubes in the samples. And it should be the worst case they can have. So we just output all 10 possible cubes. That's the idea, but sometimes it doesn't work. Because 2 cubes, they can overlap, and that's the
But in the general product distribution setting, if we have some kind of a lower bound on the density, we'd be able to do something similar in that case. Using this mixing boundary.
So what's the problem?
So essentially, it's the distribution itself is say non-uniform. You have a non-uniform product distribution.
Oh, I see.
With a lower bound of the density. So like the distribution is such that, let's say, the density is above some parts, let's say half.
Yeah, we actually think about this problem. So the genre, this product is one problem. And the thing is, there is a very simple case that we can deal with in our algorithm. So suppose the distribution in each direction is 1D Gaussian, bounded 1D Gaussian. So we have to remove tail of the Gaussian. Now it's bounded by -1. And for a uniform distribution, the good thing is the difference of the TV distance always come up with as the boundary. So if we draw 2 uniform distribution, you can see the only difference are at boundary. But if you draw 2 Gaussian, the difference will be all over the whole interval. And the middle part is hard to deal with. We can't remove all points in the middle. So most of the points in the middle are good points. So it's hard to remove those outliers or bad points. Yeah, that's one reason we can directly apply why we can directly apply this algorithm to the other product distribution.
We have this for you.
Thank you.
Thank you for coming. We have lunch outside. Thank you.